afternoon, everyone, and welcome to Stanislaus State Science Week. My name is Sunpreet Kaur.
And I'm Chelsea Flores. We're part of the Science in Our Community team here at Stanislaus.
Stanislaus State is pleased to provide the community with opportunities to learn by engaging in live activities and pre-recorded activities that will be shared throughout this week through Zoom and through our Science in Our Community YouTube channel.
Before we start, please note that this event is being recorded and we'd like to ask for you to stay muted unless called upon by our presenter. Additionally, to keep this activity safe and fun for all, please only use the chat to answer or ask questions. Again, unless stated by our presenter, if you can unmute. So, thank you.
And now it's my pleasure to introduce our activity, Solar Observation with Dr. Morsony.
Hi, everyone. Hopefully you can see me. So I'm Dr. Morsony. I'm a professor here at Stan State, and I teach physics and astronomy. And I'm an astronomer by training. So really what I work on is like blowing up stars. I do simulations of supernova and other things that blow up. And so, boy, there are a lot of you out there, it looks like. So great. You get to listen to me for a while. So today, I am out in our little dome on campus here where we have our solar telescope located. And let's see, trying to get it in the camera. Yeah, there we go. So it's really, we have two telescopes here that are both pointed the same direction. And they're really specially made for solar observing. So a few warnings before we start. One, don't stare at the sun. It will hurt your eyes. Two, don't ever look at the sun through a telescope because it will burn your eyes and permanently damage your vision, and it will do it fast. So we can use these because our telescope here has this special filter in front that blocks almost all of the light. And then our other little telescope here, it's specially made just for solar observing. So it only lets through one specific wavelength of light, one color, and blocks almost all of the rest of the light. If you have eclipse glasses, then you can look at the sun with them, but don't like put them on and then look through binoculars or a telescope or something, because this is what happens. They will melt. And this took about 1/10 of a second to melt that hole in it. So only, if it's a special telescope with the filter at the front to block the light. Okay, so I've got some cameras hooked up here. So I'm going to bring up an image of the sun, what it looks like right now, and we'll see how that goes. If I can share. And sorry if you can't hear me, I'm kind of moving around the dome. I'll come back and get closer in a minute. Yeah, there we go. So what you can see here, and it may help if you try to zoom in or, those kinds of things. I can never get it to share, full screen or rotate or whatever from my phone. This is just from an iPhone camera. So what you see there is the edge of the sun on the right side of the screen. And you see that black spot there? That's a nice whopping big sunspot. So the sun is always changing. It's always like boiling away. It's active. And recently, this year, it's kind of getting more and more active and will continue to for the next few years. So right now, there's actually a bunch of sunspots on the sun. And one like that's probably like 2 or 3 times the size of the Earth. It's really quite big. I'll see if I can move around. There's some other sunspots on the sun right now as well. Let's see. Yeah, there's a couple there. Maybe one further. Oh, maybe that's some dust towards the bottom. Let's see. There's another one kind of on the bottom of the sun, or bottom side. Let's see. There may be some up higher. So just kind of moving the telescope around, see what we can see here. Not so much there. And there's our nice one that we started with again. So some of these spots are dust, but that one in the middle, the one that moves when I move the telescope, that's really a spot on the sun. And where you have those sunspots is where the sun's like really magnetically active. The sun has a magnetic field like the Earth does, like we have a North Pole and a magnet will spin around and point north. Sun has magnetic fields too, but they're much more active and they change a lot faster. So where you have that sunspot, you have a concentration of magnetic field, and the sun will actually be a little bit colder in the middle of the sunspot. That's why it looks dark. The surface of the sun is maybe 5,800 degrees Celsius, so about 11,000 degrees Fahrenheit. Where you have those dark spots, maybe they're a little bit colder. Maybe it's only 9,000 degrees Fahrenheit. So still really hot, but not as hot as the stuff around it. And so here we're seeing the sun in white light. So this is, we're blocking most of the light, but it's all the different colors coming through. So the sun still looks kind of yellow. The sky still looks a little bit blue. But I'm going to switch to the other telescope we have here, and it's going to be a narrow band image. So there we're getting just one color of light, red, and that light is actually coming from hydrogen atoms. The sun's mostly made of hydrogen and helium. So if we focus on this one color that's being emitted by hydrogen, then we can see some more of the structure of the sun. So I'm going to bring that up and we'll see what that looks like. And as I'm going, please put questions in chat. Our Science Week helpers here will hopefully shout out when there's questions for me. But let me switch cameras for a bit. Yeah, so here is the sun, and I'll zoom in a little. There we go. So that's the sun where we're just looking at this one particular color. There we go. And let's see, and I'm going to see if I can get that a little bit better just on my screen. There we go. And it's a little tricky to pick out on this or at this level of zoom. But if you look around the edges, you can see they're kind of fuzzy. And you can even see some places where it looks like there's little things sticking up around the edge, like on the left side of the screen. I can kind of see two sort of on the top, sort of maybe about 10 o'clock, 10 o'clock or so. There's sort of two of them. Those are, we're actually seeing these like magnetic fields are holding stuff up above the surface of the sun. And so these are like called prominences. They're like parts of the solar atmosphere that's sticking up above the rest of the sun. Let's see if I can zoom in a bit more. And then move around some. Sort of getting to sort of the limits of what my camera can do here. Let's see. Yeah, there's some nice ones. Yeah, so kind of on the edge there. And the camera is kind of fighting the focus of the telescope and everything. But yeah, you can definitely see like right on the edge there. And then there's another one a little above. Oh, hey, a bird just flew past. You can see those like kind of fountains of plasma of this hot stuff in the solar atmosphere going up and coming back down. And it doesn't quite show up on the camera, but if you look at the surface of the sun, it'll have, it's like boiling away all the time. It's just like if you're boiling water or you have like hot oil in a pan, it'll have some parts where there's stuff coming up and some parts where it's going down. And you can, with a narrow filter like this, start to see this like pattern on the surface of the sun that's called granulation because it looks grainy. And where those grains are will change with time. And the kind of overturn time is about 5 minutes. So, you'll see a pattern and then by 5 minutes later, it will have rearranged itself. So please, as we go, ask me any questions about anything about astronomy, whatever you like. I just wanted to show some nice pictures here. And then I have some slides with some pictures from space that we can see more of the sun. If you get above the atmosphere, you can see it in the UV. So I can show some of those as well. Ooh, can I explain what a solar flare is? Good questions. Okay, so let me take that one first. Yeah, so that's a great question. Let me actually bring up a nice video of that. Okay, so I'm going to stop sharing that one. I'm going to share my screen. And let's look at a nice video of a solar flare. Yeah. So this is a video from a solar flare that happened last year. What a solar flare is, so we've got this sunspot where we have this like really strong magnetic field. And that magnetic field will kind of get twisted up. And you can think of it as like twisting a rubber band. But then eventually that rubber band will snap. And when that happens, you can get this big solar flare. So you get a release of like particles and really high energy radiation. And there you can see one. Here's one from a couple of days ago. if I play the movie, you can kind of see, and you can even see these, like in this particular band in the UV, you can see these loops of magnetic field in the atmosphere. And then you can kind of see all of a sudden there'll be this flash going along it. It kind of lights up. So those solar flares are coming from those magnetic fields. And when they kind of break and rearrange themselves, they release a bunch of energy. And then, oh, and good question about the radios. I'll come back to that one in just a minute. So how does the telescope show the magnetic field? That's a really good question. Some of it, if we're looking in the white light, we can see the sunspot just because that magnetic field will kind of, it sort of holds stuff on the surface of the sun longer, and so it has some more time to cool off. But with a picture like this one, where we're looking in the UV, we can really see this magnetic field. In fact, let me go up to a previous image here. Let's see, here's one. So this is the sun over like the last day or so. You can see, like on the edges of the sun, you see these magnetic fields between these bright spots. So those bright spots are where you would have sunspots. I think the one that we're seeing in the telescope in white light is kind of over here somewhere, like that one or this one. So you're seeing it because there's hot gas that gets trapped on those magnetic field lines. So just like kind of, iron filings with a bar magnet get trapped, but they're hot. And so you're seeing that hot gas, and it's radiating this, particular atom will give off one wavelength of light. So if you look at just that wavelength, then you can start to see the magnetic field. So same thing for our red image here with our telescope, because it's looking for that hydrogen that's up in these little fountains above the sun. It's seeing them because they're trapped in those magnetic fields. And let's see, what else do we have? What's the sun's atmosphere made of? Okay, so I'm going to come back. Let's see, we've got a couple on affecting our radios and is it harmful or bad for the Earth? These solar flares they can definitely have an impact on Earth because they're putting out all this high energy radiation. And sometimes they'll also send like a big blob of material coming at the Earth, which maybe I have some video of. Let's see. Yeah, here we go. This is going to show from, several years ago. You get a big solar flare, and then your camera kind of goes fuzzy because you're getting all these like cosmic rays coming and hitting you. Then you also see, if you zoom out from the sun, and so now you're looking at much bigger scale, you get this big blast. But you also get this kind of like, it looks like an explosion coming out in that last one in blue. You see this kind of, a little bit after it gets fuzzy, you see all this stuff coming out. So that's really this flare giving you like an explosion coming from the sun, and it pushes stuff off that comes towards the Earth. And when that hits the Earth, most of it actually gets deflected away because the Earth has a magnetic field, but some of it will get like trapped in the Earth's magnetic field, and then it can actually come down and hit the atmosphere near the North and South Pole. And that'll give you like the Aurora. It'll give you the northern and southern lights. Also mess up the atmosphere, so it can like, those cosmic rays will help to ionize the atmosphere, make it more conductive rather than neutral, and then that'll make radio waves bounce around different. It can also be really bad for satellites. If you get a really big solar flare, satellites can get fried and shut down, at least temporarily, or sometimes they're lost permanently. But you can get these nice displays also where you get northern and southern lights. Depending how hard the Earth gets hit will kind of depend on how far south they go. If you live in Alaska, especially when the sun's more active like it is now, you might see something like this, every week, or maybe for a few days, and then a few weeks later for a few days. If you live, far north in the United States, like in Minnesota or something, you might see this a few times a year. If you live where we do, probably not going to see it very often, maybe once a decade. A little further north in California where we are, maybe every few decades. It really has to be, a huge outburst coming at the Earth to get something like this. Let's see, what other questions do we have? Oh, do solar flares happen daily? It depends. Right now, yeah, there's probably at least some small solar flares each day, and there have actually been some big ones recently. The more sunspots we see on the sun, the more likely there are to be solar flares. But the sun will kind of become more active and then less active. And it does that about every 11 years. Like in 2014, 15, the sun was really active. Then it's been really low activity for several years, and now it's starting to get more active again. Like if I go back, I know this is a neat video, right? But let me see if I can go up. Here was, our sun a year ago. And okay, there's a little bit of bright stuff, and there was like one solar flare that day, maybe a couple of little sunspots. If we looked at it a year before, when we did Science Day, there was like nothing at all. If we look at it now, or a couple of days ago, you can see there's a lot more activity. You see a lot more of these big loops of stuff. You see a lot more bright spots, which in this color, the sunspots are going to look bright. So that's what you're seeing, looking a lot more active. And as time goes on, it'll get even more active. So in some years, you're seeing a bunch of solar flares every day. Some years you see hardly any. Maybe it might be several weeks between solar flares, or at least between anything worth noticing. There's always kind of tiny little things going on. And do I have a good picture of that? Let's see. And this is a picture kind of the sun over a solar cycle. So from kind of the minimum going up where there's almost nothing, going up to the maximum where there's a bunch of stuff. And we can count the number of sunspots to kind of keep track of this cycle. So yeah, somewhere here, this is in the red is like how many sunspots there are each year going back 150 years or so. And you can kind of see this repeated pattern where there'll be almost none some years, and then there'll be a lot. And now, kind of 2020 was about the low in the current cycle, and now it's starting to pick back up. And the peak will probably be around 2025 or so, 24, 25. So the next few years, you'll get a lot more sunspots. If we look at the sun again next year and the year after, there's a few sunspots today, there'll be more probably, and more flares and more activity. Oh, what's the sun's atmosphere made of? Yeah, good question. So the sun is mostly hydrogen and helium. So these really light elements, so like helium, helium balloon, and hydrogen it's in water and sugar and lots of stuff, but on its own, it's just a very light gas. 98% of the sun is hydrogen and helium, and then 2% is everything else, like oxygen and carbon and iron and calcium and all the other elements. So it's almost all these light gases. And it's all very hot, so it's mostly, it's all single atoms, and a lot of those are ionized. So in the atmosphere, you get a lot of this very hot gas, a lot ionized, so you have like free electrons and then ionized atoms as well. Does the sun have an atmosphere? Yeah, so the sun is kind of all gas. So, in some sense, it's all atmosphere. But there's kind of a layer down in the sun that we can see to that we call the photosphere. And that's sort of what we would call like the surface of the sun. And here was what it looked like a day ago or earlier today. That's kind of where we'll see the sunspots and a little bit of activity. That's kind of where most of the light's coming from. But then if we make these narrowband images, just like the Earth has, kind of the atmosphere air gets colder as you go up, like into the mountains. And then if you go up really high, it'll start to get warmer again, and you have like an ionosphere on Earth. Same thing happens in the sun. If you go up a little bit, it'll look, and this is a narrow image, it'll look more like this. So here you can really see that granulation on the surface of the sun. You can see it boiling away. You can see like these prominences and that sort of stuff. And I think that's where it's actually a little bit cooler, although this is where it's starting to heat up again. Then you go to a bit higher and you have a hot atmosphere. So this is like ionized gas, a few 100,000 degrees. And that's where we're seeing these loops of magnetic field and the sunspots look bright. You can see flares and stuff. And then you can go up even higher in the sun's atmosphere. and it's a few million degrees. So this is like X-ray emitting gas. This is really hot stuff. And this is, you're really kind of looking at the solar wind coming out in some sense. So you can see bright spots still. You can even see like this kind of hole in the middle of the sun where it's dark. That's where there's actually really fast solar wind coming out. So there's less stuff there. And it looks dark, even though there's actually more high speed stuff coming out. Oh yeah, the Aurora video clip I used, that was sped up. So that was like a time lapse. But you really, you can really see it change when it happens. I've only seen the Aurora in person like once, maybe, or twice. I actually used to work on it when I was an undergrad. I worked on data from a satellite that was looking at the Aurora from space. So I saw it, every day because we get new images every day. But in person, I used to live in Colorado, so I saw it once there, or maybe twice. And then it was kind of solar minimum after that. So then there wasn't very much Aurora that far south. And then I lived in Wisconsin after that, where when the sun's active, you can see Aurora, quite a bit, several times a year. But it was when the sun was quiet and at solar minimum, and so I never got to see it there. And then by the time it was at the last maximum, which is around 2014, I'd moved and I was living in Maryland, which is about as far south as we are. And so I couldn't see it anymore. Let's see, which questions am I missing? Why do they change color? Oh, do you mean why the Aurora changed color? Yeah, that's really interesting. The Aurora is made by these high energy particles. They kind of will come from the sun. They get trapped in the Earth's magnetic field, and then they'll sort of rain down into the atmosphere. If we take a look at an image of it, let's see, like this. So then those particles come down into the atmosphere and they hit the molecules in our atmosphere and they'll make them light up. And what color you get depends on what type of atom is getting hit. And so I never remember which color is which. I think the green is oxygen, and that's kind of a bit further down in the atmosphere. And then the red is nitrogen, but like individual nitrogen atoms that'll be higher up in the atmosphere. I might have that backwards. So the pink will kind of be higher in the atmosphere, the green's a little bit lower. And it'll kind of depend on the energy of the particles coming in, how far into the atmosphere they get before they hit something. And that can give you those different colors. Oh, why is the sun more active some years compared to others? Honestly, we really aren't sure. That's sort of an open question. Some of it has to do with kind of the sun boiling away, because the sun's like, it's called convection, and it's like overturning. Like the same thing will happen in under the crust of the earth, like magma comes up and makes volcanoes and then kind of spreads out and you get like plate tectonics. Same sort of idea inside the sun, where the outer part of the sun overturns, but it does it a lot faster than the earth. So it happens like every 11 years or so. And that seems to be related to, okay, at some parts you get more magnetic field and at some parts you get less. But we really don't know why it's every 11 years. We really don't know why, why is the activity linked? I mean, the magnetic fields are created by this overturning, but why does the amount of magnetic field go up and down? It's kind of in motion all the time. So we aren't really sure. And that's an active area of research, like solar physics research. That's one of the things they work on, is trying to understand why do we have a solar cycle. And we aren't really sure if other stars have solar cycles. We can look at other stars and we can't really image the surface like we can the sun, but we can kind of tell how active they are. But it needs a lot of observations to figure out, is there a cycle like that? So we don't really know that well for other stars. And we don't really know, okay, maybe we see it get more active and less active, but then does it, come back up again? How long are those cycles? Are they shorter or longer? That's also a big area of research. Ooh, how many solar flares can the sun have at one time? And are solar flares dangerous to humans? The sun can have a bunch of solar flares at once. If you have a bunch of sunspots, you might get, several per day. And, some can be big and some can be small. So the biggest solar flares are, called like X-class solar flares. You could have like a few of those a day if it's a really nice active sun. And are solar flares dangerous to humans? So on Earth, not really, at least not directly, because we're protected by, well, one, we're protected by the atmosphere of the sun, the atmosphere of the Earth. So the particles coming from the sun, they hit stuff in the atmosphere. They don't hit us directly for the most part. And second, we're protected by the magnetic field of the Earth. So most of, even when you have those big, it's called a coronal mass ejection, CME, this big explosion from the sun coming at Earth. Most of it gets deflected around the Earth, and what's left just gets trapped in the Earth's magnetic field. It doesn't hit the Earth directly. But if you're an astronaut out in space, then yeah, these could definitely be dangerous. And especially if you're out, if you're just orbiting the Earth, okay, then the magnetic field still protects you, even though you don't have the atmosphere anymore. But if you're an astronaut on the moon or somewhere, there's no magnetic field, then yeah, it's definitely a big deal. In fact, I think it was, I'm trying to remember which one. I think it might have been actually Apollo 11, like the first moon landing. If they had gone about 3 weeks later, there was a really big solar flare. And if they'd been, around the moon or on the way to the moon when that happened, they probably all would have gotten cancer from that, because it would have been so much radiation that would have hit them. So kind of knowing what's the sun going to do if you're sending astronauts away from the Earth is important. And even if it's not hurting people directly, these solar flares could still cause damage. If you get really big ones, well, they can knock out satellites and stuff, but they can also knock out power, because they're so powerful, they kind of mess up the Earth's magnetic field, and that'll actually cause like currents and power lines. So I think there was a blackout in Canada and like on the east coast of the US back in the 70s that was caused by a big solar flare. It like knocked out power and then kind of caused a cascade that knocked out the whole power grid. And so with a big solar flare, that can definitely happen. And going even further back, the biggest like solar flare and solar storm that we ever had, or that we've seen in modern times at least, was back in 1850, I think. And back then, they were using telegraph wires. And it was actually so much power that was going through those telegraph lines that actually it like blew out transformers, and it started fires in some of the telegraph stations. We had a bunch of like this paper that they used. You had like ticker tape, like paper going through the machine. Some of that lit on fire. A really big solar flare like that, if something like that happened today, it could knock out power a lot. It could knock out a bunch of satellites in space. It could really cause a lot of disruption, even though it's probably not directly harmful to people. Let's see. Oh, I guess also if you're flying in an airplane, especially if you're going like over the North Pole and there's a big solar flare or a big, if the Aurora is happening, then some of that radiation is hitting you. It's like for flight attendants, it can be bad, kind of in the long term. Let's see, what else do we have here? Oh, in the pictures, what does the nanometer and K-kilometer mean? What do they represent? Good question. Let's see. That was probably back on some of these, right? So I forget which one that was. Oh, yes, right. On like the one, not this one, but a couple back. Yeah, so here, this is, so like the 21.1 nanometers, that's the wavelength of light that this is showing. So you have, this is from a spacecraft. So it's out in space. It actually sits between the Earth and sun and stares at the sun all the time. And it has a bunch of these different filters to take images of the sun. And so this is way out in the ultraviolet somewhere. So 21 nanometers, I forget what this is. This is probably looking at like ionized helium in the atmosphere of the sun or something. So that's just for me to remember what wavelength it is. And then the like 2 million K, that's the temperature in Kelvin. So Kelvin is the temperature scale scientists use. And each degree is like the same as a degree Celsius. But instead of 0 being where water freezes, on the Kelvin scale, 0 is absolute 0. And then water freezes at 273 Kelvin. Water would boil at 373. So this is, millions of degrees Kelvin. This would be like 3 million or 3.5 million degrees Fahrenheit. This is this really, really hot X-ray gas. And then as I went back and we get kind of closer to the surface of the sun, it gets cooler. And I don't know, don't pay attention to the wavelength. That's just whatever this thing was. Yeah, this was, this 30 nanometers back down to 50,000 degrees. And then looking at kind of just above the surface of the sun, this is only 5,000 Kelvin, which I think is about 11,000 Fahrenheit. Yeah. And this is more of a white light image of the sun. So this is what the sun looked like yesterday or earlier today. So I think that's that sunspot that we were looking at. A lot of this kind of fuzziness on the edges is probably coming from these other sunspots over here that are sort of rotating around the side of the sun. Why would it burn your eyes to look at a solar eclipse? Oh, yeah. If you have a solar eclipse, that's like the moon moving in front of the sun and blocking the light from it. If it's a partial eclipse, it'll get darker, but still some of the sunlight is coming to your eye, and the sun's really, really bright. So even if like the sun's 99% covered by the moon, that's still bright enough easily to hurt your eyes. If it's that's when you want to use your like eclipse glasses when it's a partial eclipse. If you're lucky enough to really see a total solar eclipse, then you can take your eclipse glasses off because you're not seeing any of the sun anymore. But what you do see is this extended atmosphere of the sun. So you really see this, you can see this highest layer of the atmosphere, the corona that extends out. And I actually got to see a solar eclipse. It was awesome. The one in 2017. So once the sun is covered, it looks like totally black. But then you see these big rays of light still coming out from the sun. And what you're really seeing is that corona. And that you can look at just with your eyes, because that's not that bright. Maybe I have even a picture here of a solar eclipse. I forget. Here we go. Yeah, here's, this is not my picture. This is somebody's much better picture. So you can really see that, like that's what it looks like to your eye, where you see this, stuff coming out where there's more or less active regions. You can have more stuff coming out. So that looks really cool. But you have to be careful because the total eclipse part only lasts like 2 or 3 minutes, depending on the eclipse. And if you're still looking at the sun when the total eclipse ends, then it's going to hurt your eye. Because one, now you're seeing some of the sun and it's going straight into your eye, and your eyes are adjusted for the dark because it's dark during the total eclipse. And now all of a sudden it's super bright. So that'll hurt your eyes. So you kind of have to know like how long is the eclipse going to last from the spot that you're standing. And, a few minutes before that, make sure you look away from the sun or put your eclipse glasses back on. So so like during a total eclipse, you could take the eclipse glasses off, but otherwise you want to use them, or use like a pinhole camera, like cardboard, and poke a hole in it, and then you can look at the shadow on the ground, that kind of stuff. Excellent question here. So how long does it take for a solar flare to happen and then affect the Earth? That is a really interesting question. So let's see if I can go back to my nice solar flare video. Sure, here it is. So the solar flare is really fast. I mean, it's only a few seconds to get that blast. And then, I don't know if you can even see the time delay on here, but those particles are getting to Earth almost immediately. So those kind of cosmic rays, they're going almost the speed of light. They'll arrive really, really quickly, like within, a few seconds of the solar flare. But the big like explosion part that then comes to Earth and will make the aurora and really does the most damage to satellites and everything, that'll take a few days. So it takes like 2 or 3 days to get to Earth. The fastest ones maybe take less than a day if they're really, really fast and high energy. Slower ones, maybe 3 or 4 days. So those you have a little bit of warning. And part of why we have these satellites looking at the sun is to look for these big flares and these big explosions coming at the Earth. So then you can do things like you could put your satellites into safe mode, or point them away from the sun. You can redirect airplanes. So if they know there's going to be a big CME, a big coronal mass ejection arriving at Earth, they'll not let planes fly over the North Pole. They'll make them go further south so that they don't get as much radiation. You can, get your power grid ready if it's a really big one, kind of make sure you're ready in case things start, tripping or transformers start blowing up. You can reroute power. Yeah, the flare only lasts a few seconds. Particles will arrive, within a minute or so, or start arriving, and that's where you're getting all this fuzziness. It's a bunch of cosmic rays hitting the camera, and then a few days later, that big explosion reaches Earth. Because it's not going at the speed of light. It's a lot slower, but still, Earth to the sun in a few days, it's fast. Let's see. So let me know if there's any questions I missed, or if you have any more. But I think we're almost to the end. But if there's any last question or two, I'm happy to answer. Also, if anyone thinks of any more questions, you're welcome to get in touch with the organizers, and they'll pass them on to me, and then I'll email you back and respond. Can the CME get matter into the atmosphere? Yeah. So it won't directly hit the atmosphere, which is actually really fortunate because it would do a lot of damage if it did. That's because the CME is magnetized, it has its own magnetic field, and the Earth is magnetized. And so it'll get deflected. So satellites in orbit, like far from the Earth, it can hit them directly, but the ground and our atmosphere are protected by that magnetic field. But then some of the particles from it will hit the atmosphere because they get trapped in the Earth's magnetic field. Not most of them, but 10%. And then they'll kind of stay in the Earth's magnetic field a while, and then they'll come down and hit the upper atmosphere, and that's what's giving us aurora. If we didn't have a magnetic field, it'd actually be really bad because it would hit our atmosphere directly, and it could actually strip the atmosphere off of the planet over a long time. And we think that's actually what might have happened to Mars. Mars has only a really thin atmosphere now, but we think in the past, 4 billion years ago, or 3 billion years ago, it might have had a much thicker atmosphere like the Earth does. But Mars doesn't have a big magnetic field like the Earth. So the atmosphere actually got eroded away over time. It got hit with so much solar wind and so many CMEs, it stripped the atmosphere off the planet. Will our sun explode? Will our sun explode? So our sun won't ever really explode. Our sun won't make a supernova where the whole sun blows up. It will, though, at the end of its life, it'll get a lot bigger. So it'll become a red giant. And eventually it'll actually become maybe big enough to swallow the Earth. It'll be about as big as the Earth's orbit around the sun. And that'll be kind of when it's burnt up or it's burning up the last of its fuel. But at the end, it won't really make a whole explosion, but it will lose most of its atmosphere. So most of the outer part of the sun will kind of get blown off and be a really, really massive solar wind over a few tens of thousands of years that'll get lost to space. And then that'll be about half the mass of the sun. And then the other half will stay together, and that's will be just the core of the sun. And it'll burn up the last of its fuel and then just kind of die and end up as a white dwarf. So what is the most amount of time someone could look at the sun without damaging their sight? I would say 0. You should really not be staring at the sun. Okay, if you glance, and definitely not using a telescope or anything. If you just sort of glance at the sun really quickly, it'll probably leave a spot in your vision, but you'll recover. If you were holding your eyes open and staring at the sun, certainly in a few minutes, it's going to damage your vision and maybe permanently, but even less than that, even a few seconds could start to damage your eyes. So yeah, don't stare at the sun. Unless you have, your eclipse glasses or something special. Even with just regular sunglasses, don't stare at the sun. Then, okay, maybe you can stand it, it doesn't hurt for a few seconds, but you could still be getting like UV light, or, it can still be hurting your eyes. It can still leave spots behind. So yeah. So let's see. Well, so I think we're at our end time. And I know there's another event starting at 3, I believe. So I'd better let our helpers and everyone go. But if you have any more questions, please, send them to me about the sun, about astronomy, anything you'd like, or send them to Chelsea or Supreet, and they'll pass them on to me. So thank you, everyone.
Thank you, Dr. Morsony, and thank you everyone for joining us for the solar observation activity. Science Week would not be possible without you and the dedication of our faculty, staff, and students here at Stan State.
Thank you so much for watching. Please follow us on social media to find more about our upcoming events.